Okay. Let us continue with wait a second. Looks my connection of the wait a second. I'm sharing with my iPad. Great. Okay. So let's start. So we're going to continue with SVM. We're going to finish the remaining a few steps regarding SVM. So in the last lecture, we have introduced the definition of support vectors, right? From solving the dual form, and also we introduced the kernels. So what are the support vectors? From solving the dual form, we know that we can represent our optimal weight vector, feature vector, right? Not feature vector, weight vector for those features as a summation, a weighted summation of the training inputs, right? Each training input, it has coefficient, which is the optimal Lagrange multiplier, and the label. The label here, yn, is either 1 or -1. So as we analyzed in the last lecture, most optimal coefficients, not optimal Lagrange multipliers, alpha n's, are simply 0. If for a particular xn, the corresponding alpha n star is simply 0, it just means that, okay, xn won't have any effect on the optimal weight vector, right? So the final weight vector is only determined by a subset of training input vectors who have a non-zero alpha n's. So those subset of training inputs are called support vectors. That's the definition of support vectors. So we can define support vectors formally as a set of input vectors whose optimal Lagrange multiplier from solving the dual form is strictly bigger than 0. Then the optimal weight vector is only determined by those support vectors, right? Their summation, their weighted summation. Yi, exactly. That's it. Right? So we have analyzed where those support vectors stay, right? So they are not stay on the they are not stay they are not staying on the outside the margin. Actually, they are either on the they are either on the margin or into the margin. Okay. Then we talk about kernels and kernel tricks. So what are kernels and kernel tricks for? I want to ask. Anyone give me a hint? So what's the motivation for us to talk about kernels and kernel trick?
We want to use inner product in the first space, not in the featured mapping space in a higher dimension.
Yeah. So the goal is that we want to generalize our linear classifier to nonlinear classifier, right? So we have the support vector machines that are originally designed for linear classifiers. But now, if we want to do the nonlinear classification, so our idea is that we're going to do some nonlinear feature transformation, right? Our original feature vectors here, through some nonlinear feature transformation, we convert the feature vector to a high dimensional space. So each element in the transform feature vector can be viewed as a nonlinear function of x. That's why we call this one as a nonlinear feature transformation or nonlinear feature mapping, right? So in this mapped feature space, we run our SVM or any other linear classifier to learn a linear model, right? And then our prediction is gonna be W star transpose with multiplying with the mapped test input vector and plus the box parameter b and take the sign, right? So this is our new prediction function. And you can imagine that because the training is conducted in the mapped feature space, so our representation of optimal bit vector, now in this weighted summation, you have to replace each input vector by their mapped vector, right? So now if we apply this representation, we do not need to explicitly write down W star, right? If we apply this representation into the prediction rule, we got sign. And this is summation, right? Because W star is essential summation. We're going to go through the support vectors, and you have alpha I star, you have yi, and you have the phi xi, the transport feature vector. It will do the inner product with the test input, right, after the feature mapping, and then plus the bias parameter and take the sum, right? So that brings up a problem, a major problem, which is computation problem, right? So as we showcased in our last lecture, right? If we explicitly do this nonlinear feature mapping and then do the inner product, it is very costly. The major issue is here, right? So in many machine learning applications, we found that only when you have like infinite dimensional feature space, you are very to get to be enough expressive. That means you even cannot practically compute this infinite dimensional mapping. How can we do that? Right? That's where the kernel trick comes from. Right? So the kernel trick is kind of a function where it contains two inputs, x and z, from the original input space. The kernel function can do all the operations inside the original space, but the computational result, it is equivalent to first do the feature mapping on x and then on z, and then do the inner product. If you can find a kernel function which can fulfill such kind of computational advantage, then you apply the kernel trick. So kernel trick is essentially a computation trick. It tries to avoid explicitly feature mapping and inner product, but doing much cheaper computation in the original feature space to fulfill the same result. Any question? Okay, great. So that's how the kernel trick is motivated. Now we want to look at the properties of kernels. Right? What kind of functions are kernels, right? Can any function of two inputs be viewed as a kernel function, a valid kernel function? And the answer is no. So let us just repeat the benefit of kernel trick, right, from our example seen in the last lecture. So you want to work with degree 2 polynomial features. I want to change back to right color. Degree 2 polynomial features Vx, right? So suppose your original feature vector is n-dimensional, right? So your mapped feature vector will be 1 plus n times n minus n plus 1 over 2 dimensional. Why? Because you have to include degree 0 terms, degree 1 terms, including all of the original features, and also degree 2 terms, right? Degree 2 terms are all the square of the original features and the cross product of different features. So you see, actually the number of the mapped features, I mean, the dimension of the mapped feature vector will be proportional to n squared, right? So if you do the explicit feature mapping for any two input vector, you do the explicit feature mapping, and then you do the inner product, the computational cost will be O n squared. Why? Because your mapped feature vector is n squared, right? If you want to do the inner product between two n squared dimensional feature vector, you have to compute the element-wise product for n squared times, right? So their summation, the time complexity will be O n squared, right? And then we can, indeed, instead compute the kernel function, which is 1 plus x transpose z x squared. We have shown that the result of this kernel function is the same as explicit feature mapping and the inner product up to different coefficients, so it doesn't matter, right? But the computational cost for this kernel function is what? What is the computational cost for this kernel function?
N.
Yeah, n, right? Because everything is done in the original feature space. You first do the inner product between x and z. They are both n-dimensional, so this is just n, right? So after you have this inner product here, the remaining thing is just constant. You just do a scalar computation. So it reduces to on. So actually it reduces 1 order of the magnitude in the computational cost, right? This is a dramatic reduction. So the kernel trick allows you to save time and space to compute dot product in the original d-dimensional space. So then the natural question would be like, now that kernel function is so amazing, right? Can any function of two inputs can be applied, can be viewed as the implementation of some kernel trick? The answer is no, right? It's not. Such kind of function must be a small subset of all possible functions of two input vectors. Not all functions two input vectors can be viewed as a kernel function, right? So then, what kind of function can be viewed as kernel function? Right? So a kernel function k of x and z is valid only if it corresponds to an inner product in some feature space. And you see that many commonly used kernel function corresponds to the inner product in infinite dimensional feature space. And then a natural question will be like, given a function of two inputs, right? So how do you justify, how do you show it is valid function or not? So the general idea is to construct a so-called Gram matrix over an arbitrary set of input vectors and show whether it is positive semi-definite. So now we're gonna look at what kind of test conditions, what kind of conditions we can use to say whether a particular function is a kernel or not. Or someone asked how much the computational cost is saved when the degree is 3. That's a very good question. I won't give you the answer. I will leave it as exercise for you. Does it sound good? So actually, later when we talk about the general case, like you have like D polynomial kernel of D degree, you can try to count how many computations you need to do the explicit feature mapping in the product. Right? And then we can look at the computational cost for the kernel function itself. It's still n, right? Then you'll see how much orders of magnitude you can save from computing the kernel functions directly. Right? So this is a very interesting problem, and I encourage you guys to think about it. It's a very good question. Okay. So now let's look at how to justify a function is a valid kernel. Right? So to do that, we need to review some basic concept called positive semi-definite matrices. How many of you haven't heard of positive semi-definites? How many of you have never heard of it? Okay, great. So I assume that everybody have heard that before because it's a fundamental concept in. Oh, okay. Yeah, anyway, it doesn't matter. So it's kind of I want to express this is kind of like a very fundamental concept. We haven't taken linear algebra course before. You must have learned this concept. So positive semi-definiteness is a property of the symmetric matrix. It's a very important property. So it's very widely used to characterize all kinds of mathematical objects in math and engineering. So what's the definition of the positive semi-definite? We call a symmetric matrix M is positive semi-definite if for any non-zero vector Z, we have this quadratic form to be non-negative. So if Z is full of zero, of course, this quadratic term is zero, right? Z transpose MZ is zero. But as long as there is one non-zero element in Z, we call it non-zero vector. So if for any such non-zero vector Z, we can show that Z transpose MZ is no less than zero, then we call the matrix M is semi-positive definite. And usually, I mean, for simplicity, people usually written it like this. So it's kind of bigger than less than, but it's not real bigger than less than. It just means, okay, it is semi-positive definite for this matrix M. Okay? So now let's look at the definition of ground matrix. So the ground matrix is constructed on a finite set of vectors. So suppose the number of vectors is n, right? So so the set of vectors are denoted by x1, xn. Then the ground matrix is a corresponding n by n matrix, where each element in this ground matrix is the inner product between the two corresponding vectors. So Jij, the element of J at ith row and j's column is inner product between the I vector and j's vector. Right? So in general, we can assume that we conduct some nonlinear feature mapping. Right? We on top of n vectors, so our mapped feature vectors will be phi x1 to phi xn, right? Or here it is here, right? So then we can construct our ground matrix on this n mapped feature vectors, right? So here I want to emphasize the size of the ground matrix is n by n. So it's only determined by the number of training examples, not the dimensionality. Because every element is the inner product between two input vectors, right? So the total size of the matrix is n by n. So a very important property of ground matrix is that it is always positive semi-definite. Why? Any idea why ground matrix is always semi-definite?
We have to use the definition of semi-definite matrices. For Z, for any Z, we should show Z transpose M. Z is non-negative.
Yeah, exactly right. We can just show it. It's really straightforward. I think it's a kind of a naive practice problem to deepen our understanding of the concept of positive semi-definites, right? So if we, in general, like, we can use a matrix to represent all the vectors, right? So this big phi represents the matrix is n by d, where each row is the mapped feature vector. So the first row is phi x1 transpose because it's a row vector, right? The second row is phi x2 transpose, and and the last row is phi xn, right? Transpose. So n by d. Suppose that after the feature transformation, the vector is d-dimensional, right? So then the ground matrix constructed on this n feature vectors can be written as phi phi transpose. So you can verify from the structure of this matrix, right? So phi transpose is phi x, where each column becomes becomes an input vector, right? So it's phi x n, right? If you do this product, is actually auto product. You can view it as auto product, right? So where each element will be phi xi transpose phi xj. So now based on the structure, we can show that for any non-zero vector, z transpose gz equals to z transpose phi, big phi transpose z, right? And this is vector, right? This is a vector. So this is essentially an inner product of a vector itself, right? So it's a square of the norm of this vector will always be a negative. So we can show that it's pretty straightforward. The ground matrix is always positive semi-definite. So what's the usage of ground matrix? So you can imagine, like, if your kernel function corresponds to a feature mapping, right? Correspond to do some feature mapping and do the inner product, right? Then if you use your kernel to construct an n-band matrix, what is the ground matrix? An idea? What is each element of JIG if you use a kernel function k?
K of xi and xj.
Yes, k of xi and xj, right? That's the definition of the valid kernel. If a kernel function is valid, it must be the calculation of kernel function must be the equal to the inner product of the mapped feature vectors, right? So that means, okay, you can construct a kernel matrix on an arbitrary set of input vectors S, right? You have a kernel matrix K. If you can show that your K is a ground matrix, then your kernel function is a valid kernel. So now to summarize, right? If you want to show a function K of two inputs is a valid kernel, so you have two approaches. First is a direct approach. Right? Direct approach is that you can find an explicit mapping, right? You can directly show that, okay, under this mapping, my kernel function is exactly phi xi transpose phi xj. That is a direct approach. But what is indirect approach? The indirect approach is that I'm gonna just a general set of input vectors, and then I construct a kernel matrix on this set of vectors. Then I show that my kernel matrix is always positive semi-definite. Then it implies that your kernel function is a valid kernel as well, and your kernel matrix is a ground matrix. Any question?
As you said, it's a sufficient condition to show K is a kernel function. Is it also necessary for a kernel function to be semi-positive definite?
Can you repeat again? I didn't get the point. What do you mean by the function itself is positive semi-definite?
Yeah. If we want to show K, it's a kernel function. K is a kernel function.
Kernel function. Okay, kernel function. Okay. Yeah. From mathematics speaking, you're right. So I think this term is kind of on Euro. So yeah, it is equivalent to say your function itself is positive semi-definite, but usually people don't know what does it mean for a semi-definite positive function. But they're essentially the same thing.
Okay, and another question is, if we have semi-positive definite function such that like a K, and it's a kernel function, is there any rule to find phi, the function phi, feature mapping?
There's no no explicit rule. You have to observe that. You have to construct that. It's kind of like art. It's not some engineering work. It's not very easy, especially for complicated kernels. It's really hard to find the corresponding matching.
Okay.
Yeah, so that's why people, I mean, for complicated kernels, people usually use this indirect approach rather than direct approach. But direct approach, well, for some kernels like polynomial kernel, for like Gaussian kernel, square exponential kernel, yeah, you can construct the explicit mapping. The explicit mapping can even be infinite dimensional, but in most cases, you won't be able to find such mapping. Okay, so I want to read someone's asked question. What are the ways to show that we have a kernel matrix to be positive semi-definite, right? That relates to the properties of the semi-definite matrices, right? So from the linear algebra, if your matrix is positive semi-definite, that means all of its eigenvalues must be non-negative. It also has many other properties. Like from definition, you have to show that for any non-zero vector, this quadratic term is non-negative. Or you can do some say Cholesky decomposition. If there exists Cholesky decomposition, is positive semi-definite. All kind of stuff. So you have a lot of properties you can use to show that, but those are mathematical properties, and we need to look at the list of these properties. Does it make sense? Okay, so let us summarize the second approach, the indirect approach. This is called the Merciless Condition. So the Merciless Condition says that suppose we have a function of two inputs who maps two n-dimensional vectors. So the inputs must be the same dimension. X and Z must be the same dimension to a real number. And K is a valid kernel if for every finite set x1, x2 to do say xn, right? You can, and for any choice of real value c1, c2 to cn, we have this double summation to be non-negative. So what does this double summation mean? It is essentially the quadratic term. C transpose to C. You can verify it by yourself. Right? This is the definition of the quadratic term. So the vector C here is C1, C2 to Cn, and K here is just the kernel matrix over this n inputs. So if you can show that your candidate function satisfies the Merciless condition, then you can claim your candidate function is a valid kernel function. This is often used to show the function is a valid kernel. Okay?
One question.
Mm-hmm.
As we know, if the gram matrix is positive semi-definite, then K is a kernel function, okay?
Mm-hmm.
But if K is a kernel function, then is it true that always the gram matrix is positive semi-definite?
Yeah, of course.
Okay.
Yeah, it's always, yeah. It's kind of, yeah, more rigorously you should say it is if and only sufficient or sufficient necessary. Okay. Someone asked why Z not represented in the formula. So Z, Merciless condition Z is equivalent to C here, right? Doesn't matter. It just means, okay, if Z, for any non-zero vector Z, you have this Z transpose KZ to be non-negative, right? So here, the same thing, right? Just replace Z by C, right? If Z is 0, then it must be 0. Right? So in general, you can summarize the two cases into one. Like That means for any choice of real value C1 to Cn, you have this quadratic term to be non-negative. Does it make sense? Okay, so let us continue. So now I want to give you a few concrete examples, common use kernels. So polynomial kernels. Right? So the simplest polynomial kernel is just the linear kernel. It's in a product between x and z. That's it. That means, okay, I don't do any feature mapping, or in other words, I just map myself to myself. That's it. So it's called linear kernel. But then we can easily extend this linear kernel to a polynomial kernel of degree d. That means I first compute the inner product between x and z and take the power of d. So if you expand this kernel function value and try to find the corresponding feature mapping, you'll find that this feature mapping contains all the deep order interactions between the terms. If you instead first ask the inner product between x and z plus with c, and then take the power of d, then you do the feature mapping. You find the feature mapping, and you will see that okay, the mapped feature vector contains all interactions of order d or lower. So it's again, I'll leave it as an exercise for you. It will be very interesting to find those corresponding feature mapping and see how those new feature terms are constructed out from the older ones. So another very common used kernel is called Gaussian kernel. Okay. So the computation of Gaussian kernel is very similar to the standard Gaussian distributions density. So except that it doesn't contain those constant factors. So it also referred to as RBF kernel, radial basis function kernel. So to compute the Gaussian kernel, we're going to first compute the square distance between the two input vectors. So x minus c, and take the square norm. This is a square Euclidean distance, right? And then you divide this square Euclidean distance by a free parameter c. C must be positive. And then you take negative of this value, and then take exponential. It will be the kernel function value. Right? So c is a free parameter, which is also referred to as the kernel parameter, and people often call c as length skew. So you can imagine if c is very small, like c equals to 0.01, you can imagine like a little bigger distance will end up with very large number, right? This large number will become very large. Then you take exponential negative of this number, it will be approximately 0, right? So only the diagonal elements in your kernel matrix, which have 0 here, because the diagonal elements is x minus x, right? So 0 and over c is 0, so you take exponential term over negative 0, and that was 1. So when your length scale c is very small, your kernel matrix is approximately an identity matrix. You can verify afterwards, right? So if your c is very large, say c equals to 100. Right? If c equals to 100, you can imagine like all kind of distances which are smaller, much smaller than c, will end up with a smaller fraction, right? Very small fraction. You take exponential to the power of it is approximately 1, right? And then your whole kernel matrix is approximately a unit matrix where all the elements are the same. Okay. So Gaussian kernel is even more widely used than the Gaussian kernel is even more widely used than polynomial kernel. And actually, in many cases, you'll find that Gaussian kernel obtains the state-of-the-art performance. So I want to leave the following exercise for you. Right? Probably it will appear in your homework. So first, how to prove this kernel is a valid kernel. Second, how do you find the corresponding feature mapping? So here I give you a hint. The feature mapping, which is equivalent, and after doing the feature mapping and doing an inner product, which is equivalent to this Gaussian kernel, this feature mapping is infinite dimensional. That means you cannot practically compute this infinite dimensional feature vector, but you can, but mathematically speaking, you can still derive it. Oh, someone asked if Z is a parameter. No, Z is the input of this Gaussian kernel. So any kernel function is a function of two inputs. It's not a function of one input. So X and Z are both inputs of kernel. So you're going to compute the difference between X and Z and take their square norm over C. C is the parameter of this kernel function. Does it make sense? Okay. Any question regarding those examples? Okay. So suppose now you are given a set of kernels, right? Hello, can everybody hear me? Okay, great. So suppose we have a set of kernels in hand, right? So how do we construct new kernels, right? We do not want to design a kernel function from scratch because it's not trivial, right? So here are a set of rules, right? You can construct new kernels by combining those set of rules, so you end up with very complicated kernels. So if you have an old kernel, which is valid, then you just multiply the kernel with a positive constant, you'll end up with a valid kernel. You can multiply the kernel with an arbitrary function applied to both inputs. You end up with a valid kernel. You can embed a valid kernel into a polynomial function. It's still a valid kernel. Or you take exponential on that. It's still a valid kernel. So you can also add two kernel functions together to get a new kernel, or multiply them together to get a new kernel. And also, if you have some feature mapping in your hand, right? You plug in this feature mapping as the input for a third kernel, you construct a new kernel. If you have a symmetric positive semi-definite matrix, and then the kernel function, this projective form is also valid kernel. So X transpose A X prime is also valid kernel. Okay. So now I have finished the introduction of the properties of kernels, right? So this topic wants to give you a few examples of the kernels. Someone asked examples of non-valid kernels. Non-valid kernels, well, it's very easy to construct non-valid kernels. Right? Any kernel function, if it is possible to be less than 0, it must be a valid kernel. Right? And also, I can randomly join a kernel. See, let's just do sign a sign function x x minus 1 and a square norm and take sign function. It's not valid kernel. You can verify by yourself. So it's very easy to find non-valid kernel, but it's not very easy to construct a valid kernel from scratch. Any other question?
Is a logarithm of a kernel function also a kernel function?
The logarithm of kernel function?
Yeah.
No, it's not kernel function. So logarithm k, x, and y, it is possible to be negative, right? It's not valid kernel function. Why? Because you can imagine, according to Merciless condition, you need to ensure that under any finite set of inputs, your kernel matrix is positive semi-definite, right? So now, if I just give you 1 point, I just give you 1 point. If I just give you 1 point, you'll compute the kernel function on itself, right? That will be kxx, right? Then it becomes a scalar, right? The scalar is positive semi-definite if and only if the scalar must be a non-negative. Then if you take a logarithm over some kernel function, it is possible to be negative. So, so usually it cannot be a valid way to construct the kernel. Does it make sense?
Yes.
Okay. So I saw another question. Like kind of combination of kernel be invalid, but individual kernels are valid. Yeah, of course. Of course. The example we just discussed, right? Logarithm of a kernel is usually oftentimes is an invalid kernel, or sine function of a kernel is an invalid kernel as well. Okay. So now the last problem we want to address, like how do we apply kernel trick for in SVM, right, to extend it to be a nonlinear classifier, right? So actually we have everything in our hand. The extension is really straightforward. Right? So first we're gonna solve the dual form of SVM. So we know the dual form is max-min problem, right? And we have derived how to simplify the dual form. We're solving the inner minimization problem, the substitute the results into the Lagrange function. So finally, by reducing some constraints, we'll end up with our dual form to be this, right? It's a minimization, and with respect to alpha i's, right? Alpha i's, they are the Lagrange multipliers for the function margins constraints, right? So the objective will be a quadratic function with respect to alpha values, right? It's a double summation yi, yj, alpha I, alpha j, and the inner product between every pair of the input I and input j, and subtracted by the summation of these alpha values, right? So now, following the general idea where we extend linear classifier to nonlinear ones, right? We're gonna first apply the nonlinear feature mapping. That means I will do a nonlinear feature transformation over xi and xj, and then do the inner product, right? So as we mentioned, like explicit feature mapping and inner product will be very costly, so we can replace it directly by some kernel function, valid kernel function. That's it. Then we have formulated the objective for training nonlinear SVM. So now I want to ask, does this objective function have some change of the properties? Or what's the nature of this optimization problem? Any hint? Don't be scared by this kernel function. Remember, for this objective function, the formulation, I mean, the optimization task is to optimize with respect to alpha values, right? So this inner product, also the function value are just constant coefficients, right? So this is just a scalar, just scalar. That means you actually change nothing. You actually change nothing. The nature of the whole dual optimization problem. It is still a quadratic convex optimization because we are optimizing alpha values, right? So the first term is a quadratic term with respect to alpha values. The second term is their summation, right? So we still are able to call any off-the-shelf convex optimization algorithm or library to solve them. And the time complexity, computational complexity are the same. Okay, any questions so far? Is everybody comfortable? Everyone is on the same page? Okay, great. So that means if you want to implement your nonlinear SVM, you're going to first pick up a kernel function, a valid kernel function that represents some kind of nonlinear feature mapping you believe in, although you might not say what exactly this feature mapping is, right? And then you solve this optimization problem by using some quadratic convex optimization. That's it. Then you end up with a set of optimal alpha I values, right? Then you use it to recover W or not, right? And then you use the prediction, right? During the prediction, again, because we substitute W for we substitute the linear combination representation for W. So the predictions rule becomes alpha yi and phi xi transpose phi x, right? And we do the summation, we pass the bias parameter, we take the sign, right? But now, because the prediction also requires us to compute the inner product between the mapped feature vector and the mapped test input, right? We can replace this by the kernel function as well, the same kernel function. Then we finish the prediction. So now we say, okay, in the training, if we want to extend our SVM to nonlinear SVM, we just replace the inner product here in a dual form by a kernel function. And then in the prediction rule, we're going to replace the inner product with the kernel function. That's it. Any questions so far?
Is the solution for dual SVM equal to the solution for kernel version in the previous slide? I mean, if we find alpha stars for the second one, a quadratic convex optimization problem, the second one, if they satisfy also for the first one, the dual form.
Yeah.
They are a valid solution.
Yeah, they are a valid solution. Why not? It's just a computation. Just replace this explicit feature mapping and inner product by the kernel function. As long as their computation are equivalent to solving this, it's totally equivalent to solving this.
Yes, they are equivalent, but it's possible to have different solutions for each of them.
Remember, our dual form is also a convex optimization problem.
Yes.
It has a unique optimum. I mean, if it has some global optimum, it has a unique optimum, and it's not a line, right? It's not Eigen function. That means if it's a line like this, you have an infinite number of the global optimums. Well, it is possible, but if it is not like a line like this, right? It is a quadratic function. It has a unique global optimum.
Okay, so that's it. But if we find the solution for this equation, the second one, then it would be a valid solution for the first one. Then is it correct?
Yeah, of course.
Okay.
But is the valid solution for the first one with mapped feature vectors. It's not a valid solution for the problem one without any feature mapping.
Oh, okay.
Be careful at this point, right? So this one is corresponding to inner product between phi xy and phi xg, right? It is equivalent to say, okay, I'm gonna first do the feature mapping over all the training inputs, and then on this mapped feature vectors, I train SVM. It's different from like I do not do any feature mapping and then I train SVM in the original space. This is totally different. Okay, and then here I want to emphasize how to do the implementation, because you're required to do the implementation in your homework, right? So in the training procedure of your nonlinear SVM, you're gonna first pick up a kernel function, and then optimize this objective function. Where in the dual form, you replace the inner product by the kernel function, and then test you replace the inner product by the kernel function as well. So you can imagine that because we are essentially doing nonlinear feature mapping by using kernel function, then in a mapped feature space, the high dimensional feature space, you have some separating hyperplane, you have some margin hyperplane, they're all linear, right? But usually we're not able to see it. If we project those hyperplane and the margin from high dimensional space onto the original feature space, your margin becomes nonlinear. It will become some kind of curve. And if you want to view your support vectors in the original feature space, you will see that those support vectors will stay on or within this nonlinear margin in the original space. Let us look at a concrete example, right? So here we have this training set, right? We have this training set, we have blue points, say positive, and red points negative, right? So they are not linearly separable in the two-dimensional space. So apply Gaussian kernel, and which is equivalent to first transforming those two-dimensional input vectors to infinite dimensional feature vectors. Then train a linear classifier in this infinite dimensional space. So you can imagine in a infinite dimensional space, you have a separating hyperplane, and every support vector is happy to stay there, right? But if you look at the position of those support vectors in the original space, we see here is those are the support vectors. They are actually staying on or within the nonlinear margins in a two-dimensional feature space, in the original feature space. Okay. So now we have finished up everything regarding support vector machines. So you should be able to work every problems in homework 4. So if you haven't started yet, just start it. Don't delay, right? Don't rush for the last hour. Okay. So in summary, we have introduced the dual form of the SVM. So by solving the dual form, we can see where the support vectors come from. So actually, it is the support vectors who determine the final weight vector. The final weight vector is a weighted summation of the support vectors. Right? So if we represent the final weight vector in terms of support vectors, then to make a prediction, we're computing the dot products between the support vectors and the test inputs. And then we talk about how do we extend this linear classifier to nonlinear classifier by nonlinear feature mapping. And then there comes out the computational issue, because nonlinear feature mapping on very high dimensional or even infinite dimensional feature space is very, very costly. We want to avoid it. That's where the kernel trick is invented. Kernel trick is a computational trick to compute the dot product in high dimensional space. And I want to emphasize that the kernel trick is applicable not only for SVM. The same idea can be extended to perceptron. It's called kernel perceptron. So if you're interested in that, we have 2 bonus questions in homework 4, and ask you to implement a kernel perceptron and you can try to compare the kernel perceptron with the preliminary perceptron, see if there is any improvement. And actually, kernel methods is a relatively independent branch of machine learning research. So it contains a lot of in-depth content, like reproducible Hilbert space and then mathematical objects and all kinds of stuff. So it's not only some kind of computational trick there. There are many other content, many other topics in this branch, and it's still active right now. So okay, any questions so far regarding the SVM, kernel trick, and nonlinear SVM?
When you say we have infinite dimensional space, you mean exactly infinite dimension or something like 100 million dimension?
I mean infinite dimensional, truly infinite dimensional. It's not finite dimensional. If you say, okay, it's 1 million dimensional, it's still finite dimensional, although it's very, very high, right?
Oh, okay.
I mean, it's really infinite dimensional. Actually, many kernels are corresponding infinite dimensional mapping. Like Gaussian kernel is just a knowing one, a simple one. I mean, again, I highly suggest you guys to try to find the original feature mapping for Gaussian kernel. You'll see where the infinite feature mapping comes from.
Okay. Yes. And another question is about support vectors. You said they are inside the margin or on the margin. Yeah. Okay. But if we have a misclassified example, for example, one positive inside the negative part, so is it also a support vector or not?
It should be a support vector.
So support vectors are inside or outside the margin?
It breaks into the margin, right? It actually breaks into the margin and into flip into another side. We view this case as the one who breaks into the margin.
Okay, I mean an example that is outside the margin, but it's misclassified.
Yeah, that's our difference in the definition of break into margin. You mean something like this, right? So you have a margin here, right? So those are the positive, those are negative. You mean some positive showing up here, right?
Yes.
So we'll view that this positive, all the positive examples are supposed to be here. This is the outside margin, right? So if you get through the margin and run into another side, we still view it as breaking into the margin. That means the corresponding C is still bigger than 0, right? It's not C, it's alpha. It's bigger than 0, right? Why? Because for this misclassified example, you must have functional margin xw transpose xi plus b smaller than 1, right? And in this case, it must be negative, right?
Yes. It
must be negative. That means Ci must be absolutely bigger than 0.
So could you please repeat what you mean by breaking into the margin, which space, for example, in your figure?
So you have positive examples here, right? You have negative examples here. We said that we cannot ensure all the data are linearly separable. We need to allow some examples to break into the margin. The meaning is that suppose we choose these two set of examples to compute the margin. That means one outlier, this positive example, will break into the margin and even run to the side of the other margin, to the other side of the margin, right? It actually goes through the whole margin. So this example, we view as the one who breaks into the margin. We don't view it as the outside margin. Does it make sense?
Yes.
So why we it must be this misclassified example, although it looks like annoying, but it's really a support vector. Why? You can analyze it through the complementary slackness. Because from the function margin, it doesn't satisfy it's bigger than or equal to 1, right? For this case, it must be smaller than 1. For this, suppose we denote this example as xi or I. Right? In this case, it's actually less than 0. Why? Because it's misclassified, right? This product must be less than 0, right? Then, I mean, from the inference, based on the complementary slackness, you have the corresponding slack variable to be strictly bigger than 0. That means your beta I is must be 0. That means your alpha I must be C. So C is strictly bigger than 0. That means, okay, your example, the misclassified example, must be the support vector. But anyway, if you're still still a little bit unclear about that, we can discuss in more detail in office hour later. Does it make sense?
Yes, that's okay.
Okay. So now I have finished an important topic for the support vector machine, and we're gonna. Our next big topic is artificial neural nets. But before that, we would like to introduce a common used method to select hyperparameters, because this is really important in practice to help your project. I think it's necessary to mention, to introduce it right now. So we're gonna briefly introduce the cross-validation. So what is cross-validation? So cross-validation is an approach to select models. So what is model, right? What consists of model? When we get a machine learning model, we need to prepare the training data. We need to identify the hyperparameters, and then we need to minimize some loss function plus regularizer, right? So given some hyperparameter, say the C value, big C, in the SVM objective, right? We can train our classifier from the training data by estimating the model parameters, say W and B. Right? But the question is that how do we know what the best hyperparameters are? Right? So examples of hyperparameters are, say, in SVM, number of epochs in perceptron, or the kernel parameters in nonlinear SVM, like length skew parameter in Gaussian kernel, right? So one natural question would be like, can we treat hyperparameters as equally as the model parameters? Take SVM as an example, right? So we just, for simplicity, we just look at the primal form, right? So the objective function will be a half of inner product of the W itself plus hyperparameter C and the summation over the hinge loss, right? So hinge loss is max 0, 1 minus the functional margin plus B, right? So previously, our procedure is that we're gonna first choose a C value, C can be 1, and then we gonna minimize this function with respect to W and B, right? So now I want to ask, can we jointly optimize C to minimize the whole function? Any suggestion? Any idea? Like, can we jointly minimize this objective with respect to W, B, and C? Can we do that?
It becomes a nonlinear objective function, so maybe it's impossible, or we don't have any solution in general.
Yeah, that's a good point. Any other supplement? Yeah, we can try to analyze, right? So whether we can jointly optimize W, B, and C, right? So first we can observe that the hinge loss here is always non-negative, right? So the max of 0 and 1 minus function margin, right? It's always non-negative. So if we want to minimize the whole objective with respect to C, what kind of C should we choose?
Smallest possible.
Yeah, how small? I mean, C must be positive. We have assumed that C must be positive. And what is the smallest value C can choose? C can directly be set to 0, right? Why? Because I'm gonna minimize the whole objective function, and I add this regularizer with some positive term, right? So multiply with some constant, multiply with some factor C, right? And to decrease this function value, I want this positive term to be as small as possible, right? When it can be the smallest, okay, just make it vanish, right? I can set C to be 0. That's the effect if we want to jointly optimize W and B and C from this objective function. Right? But if we set C to be 0, your objective is simply this, right? Half W transpose W. It doesn't make any sense. It just has a regularizer, right? But our objective must account for the data fit, right? The hinge laws represent data fit. Right? You need to fit data, right? Otherwise, it's not training. Right? It's not called training procedure. Right? So that's a problem. Right? Hyperparameters is not directly optimizable. You cannot view them as equivalent to the model parameters to jointly ask them. If you jointly ask them, you often end up with very weird results. Then how do we select the hyperparameters? How do we find the optimal hyperparameters? Right? A very commonly used approach is called k-fold cross-validation. Right? So maybe you haven't heard them before, right? So what is k-fold cross-validation? I'm going to split the data randomly into k equally sized parts. So k is often chosen as 5 or 10, right? So we take 5 as an example. So I have part 1, part 2, part 3, part 4, and part 5, right? So to do the cross-validation, each time I'm gonna choose one part as a test and use the remaining as the training set. Then I conduct the training of the model with a particular hyperparameter, say C equals to 0.1, right? And then I test the trained model on this test set or validation set. Then we'll finish one fold. And next, I'm gonna switch to another test part, say part 4 as our validation set, and then use the remaining 4 parts as the training and use the same value of C, same choice of C to train a model, and then predict on this validation set, I get a second accuracy, right? We repeat until we test with every part, right? And train on the remaining parts with the same hyperparameter. So get this, in this example, we have 5 accuracy values. Then we take the average of these 5 accuracies as the measurement of the performance using this particular choice of the hyperparameter. So next, I'm gonna switch to another hyperparameter, say C equals to 0.2, and then I do this 5-fold cross-validation again, I got another average accuracy, right? So you can imagine if you specify a range of C values, and for each value of hyperparameter, you do this k-fold cross-validation, you end up with a measurement, right? So you just compare all the measurements to pick up the hyperparameter setting who has the best average k-fold cross-validation accuracy. Then you choose that hyperparameter as the best hyperparameter. Then you train a model on the whole data with this particular selected hyperparameter. Okay. So to summarize, right? At the beginning, we split the data into k-folds, and then we train a classifier on k-1 parts, and then evaluate on the remaining one. So repeat this using all the k parts as the validation set. So the quality of this hyperparameter is the average of these k estimates. You take the average, right? And you repeat this for this procedure for every hyperparameter choice. And finally, you select hyperparameter who has the best average k-fold cross-validation accuracy. And finally, you train a full data set using this setting. You can select the hyperparameter. Okay, any question?
Isn't it better to first shuffle the data and then use k-fold cross-validation?
The same thing. I think you're talking about the same thing. I mentioned that at the beginning we should randomly split the data into 5 or 10 folds, right? So it's basically, if you want to random split, you're gonna first random shuffle the data, right? And then you do the split. Or you can do the random selection of the training examples to form part 1 and part 2 and part 3 and part 4. They're all equivalent. Does it make sense?
Yes.
Okay. So I saw someone asked, okay, should we search for a value of C within a range to reduce computation cost? Yes. In practice, you're not able to search the entire space of the C values. Usually, you have to specify a range of C, 0.1, 0.01, 0.2, 0.5, blah, 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 and 1. Like, suppose you have 100 candidates. This cross-validation will apply to every candidate value. Then you pick up a candidate who has the best performance. Does it make sense? Okay, great. So that's all about the cross-validation. Okay. So in the remaining several minutes, I want to give a start on the artificial neural nets. Let me share the slides. So can everybody see the slides?
Yes.
Okay, great. So so what we have right now, we have seen a bunch of learning algorithms like decision trees, data boost, embedding, least mean square, perception, support vector machines, kernel SVM, kernel perception. Right? So from those learning algorithms, we have got some general learning principles, like what is the definition of overfitting, right? What's the balance of overfitting? Mystic bound learning, that corresponds to a learning perception, right? Pack learning, computational learning theory, hypothesis choices, the VC dimensions, and training and generalization errors, generalization error bound, regularization, empirical risk, minimization, right? So all of those learning algorithms, we have learned a few algorithms which can produce linear models, right? Linear classifiers. So, and also we have introduced a general trick called Kernel Trick to extend linear classifier to nonlinear ones, right? So people would like to ask, right, what if you want to directly train a nonlinear classifier? We're not trying to extend some linear classifiers, say introduce some nonlinear feature mapping and embed a kernel trick, embed a kernel function, right? So want to construct a nonlinear classifier from scratch. How can we do that? Neural networks are the state-of-art nonlinear classifiers, right? Everybody knows that they're very hot, right? Everybody equal neural networks to machine learning, equal machine learning to artificial intelligence, which I totally don't agree, but right now it is the climate, right? So we're going to introduce neural nets. Here are the topics we're going to talk about, right? So first, what is the what is the definition of neural network? How do you specify a neural network? And then we'll first learn how to predict with a neural network. This prediction procedure is called forward pass. And then we'll talk about how to train a neural network. And the training of the neural network is based upon a so-called backpropagation procedure. So you will see that backpropagation is essentially the application of the chain rule, nothing special. And finally, I would like to point out some practical concerns. Of course, we're not introducing thousands different neural nets. They are invented every minute. But everybody should know what is the K of the neural nets, how to train that, how to make prediction, how to implement. That means your final homework 5, you're required to implement a neural network from scratch by yourself. By practice, you will never need to implement from scratch. You will always depend on all kinds of modern neural network packages like TensorFlow and PyTorch. We'll plan to give some tutorial on TensorFlow and PyTorch. Okay? Does it make sense? Okay, so I would like to spend 1 minute to introduce the simplest neural network we have discussed before. Right? We call it linear threshold units. Right? It's actually a graphical illustration of linear classifier. Right? So how can we graphically represent a linear classifier? Right? So here, the bottom level are our input features. So assume we have 4 features and we have a constant feature 1, and we collect all those features and feed them to an intermediate node. So this intermediate node will, integrate all the information from all the features, right? So how does it integrate? We connect each input feature with this intermediate node with an edge. This edge is associated with a weight, so W1, W2, W3, W4, and for the constant feature, we associate the edge with the bus parameter B. Right? So the integration is done by the inner product between the weights, between the weight vector on the edges and the input feature side. So this is the dot product. Then we'll apply some threshold to generate the output. So if you represent as a mathematical language, is this function, right? The sign of the inner product between W and X and plus B. Right? And this is one neural network actually. This is called one layer neural network. And the learning of this one layer neural network has a lot of ways, right? You can use perception, you can use SVM, you can use other laws as well. Generally, you're going to minimize those laws on the data to estimate the parameters on the edges, W1 to W to B. So now if we want to extend this linear threshold units to make it more complicated, right? How can we do that? The neural network uses very simple construction rule, very, very simple. Just like you view this structure as a basic unit, you view it as a brick, right? You just construct them layer by layer. You know, it's very complicated, very flexible model. How can we do that? So, in our original linear threshold unit, our inputs comes from the data, right? Those are features from the input data, right? But now, to improve the expressiveness of this model, right, we will not use the original data as our input. Instead, we're going to construct a set of new linear threshold units. We use their outputs as the input for this particular unit. So we first use x1 to x4 and 1 to construct the first linear threshold unit. And then we use that output as the input for this particular unit, right? Linear threshold unit. And similarly, we can construct another linear threshold unit to generate second output, which serves as the second input of this linear threshold unit. You can do it again, right? You get another 4 linear threshold units to get the output to serve as input of the final linear threshold units, right? So now we have obtained a 2-layer neural networks. We have an input layer, which all comes from data. We have one hidden layer, which summarizes the results, which transform the input data, right? And this transformation are fed into the final linear threshold unit to generate final output. So you can think the hidden layer as a learning a good representation of the inputs. And this dot product followed by the threshold constitutes a neuron. Right? We usually view this as a basic node in the neural network. We just combine them together. We view it as a neuron. Right? And in this simple two-layer neural networks, we have 5 neurons. Okay, so that's a concrete example of a two-layer neural network. So on next Monday, we're gonna give the formal definition of a neural network, and then we'll proceed with the details in prediction and learning with neural nets. Okay, we stop here today.